Hello, everybody. Good morning, afternoon, evening, or night, depending on where you are in the world. Welcome to the fourth and final installment of our Networking Certification Essentials short course from IT Masters and Charles Sturt University, presented by the inimitable Ian Robertson. My name's Jack. I'll be just emceeing, facilitating a little bit. We also have Lily Nguyen in the back end, making sure everything goes according to plan. So welcome, everyone. This is the fourth and final installment, and we are coming to you from the lands of the Wurundjeri people of the Eastern Kulin Nation, as well as the Jagera and Turrbal people up in Mianjin. So IT Masters acknowledges the ongoing and unbroken sovereignty of the First Peoples of this continent and acknowledges and pays respect to their elders and ancestors and connection to the lands, waters, and culture. This short course is going to be, as I said, the final installment of this, this webinar will be the final installment of this short course, which does, of course, mean that there will be the exam coming up. So just to preemptively answer a couple of exam-related questions, the exam will be available for you to undertake within about the next 48 hours after this webinar is finished. You get one attempt at the exam. You get 60 minutes in which to complete it. The pass mark is 50%, and there will be 40 multiple choice questions, some of which will be selecting multiple options, some of which will be selecting just one option. That should be evident depending on which question it is. That exam as well, you will receive, if you successfully complete the exam with a passing grade, you should receive your certificate within about 7 days from the time of your completion. And the forums for this short course on the student portal will also close 7 days after the course has been completed. So those forums as well are a great place to engage in lots of detailed discussions with your peers, as well as with Ian, the mentor. As usual, we will attempt to answer as many of your questions tonight as possible, but if you'd like more detail than we have time to go into tonight, or if your question is not able to be answered due to time reasons, please do jump on the forums and ask those questions. Similarly, if you've got those questions that are specifically about the content of the webinar tonight, please pop those into the Q&A section down the bottom of your Zoom window. If you'd like to discuss with your fellow participants, add commentary, that sort of thing, you can pop that into the chat section, but we won't be answering questions directly from the chat section. So if you want questions answered by Ian, the place to do that is the Q&A section. We also, and we will be having several quick breaks within this session to answer some of your questions. We'll try and get through as many of those as we possibly can. And also, all of those forums, as well as the links to the exams, quizzes, other materials, etc., are available on the student portal, which you can access at learn.itmasters.edu.au. That's the place to go for your questions, queries, and discussions, as well as your assessments for the course as well. We also, hang on, I've lost my note. Sorry, everyone. Yes, so this session will run for the next approximately hour and a half. Also, it would be super, super wonderful, as we mentioned last week, if you are able to, when you're on those forums, to complete the survey that we have about your experience taking this short course. So it's just a few quick questions, and getting to hear your feedback about your experience with this course really does help us to improve and build upon all of the short courses that we run as well. So the survey is really, really genuinely important. We read it and we take it very seriously. So if you've got, any kind of constructive criticisms, or if you've got things that you would like to reflect on that are really positive throughout the course, that would be wonderful if you were able to let us know. So that is available again at learn.itmasters.edu, and Lily has helpfully dropped the link to that survey as well into the chat just now. So thank you, everybody. The exam, as Lily has said in the chat, doesn't close. The 1 week mark will be for the closing of the forums. So discussions will be closed after a week, starting tonight at the end of this session. The exam, the 7 days that was relevant to the exam is that once you complete the exam, you should have the results of that within 1 week. So 7 days after completion. It may come a little bit sooner than that, but it should happen within that time frame. So that is what we are talking about in terms of the exam. Again, as well, if you're interested, if the thirst for knowledge in your deep within your soul has been sparked by experiencing these last 4 webinars, we would be very interested in having you as a student in one of our full-length courses. So if you're interested in potentially studying a graduate certificate or a master's degree with IT Masters, finding out if you're eligible to enter the course or for recognition of prior learning for course credit, which can shorten the length of time as well as reduce the cost of one of those full-length degrees, please jump online to itmasters.edu.au and navigate to the eligibility section, or you can email eligibility@itmasters.edu.au. Fill in the form which Lily has again helpfully popped into the chat as well, and we'd love to discuss the options for you to complete one of our full-length courses. So without further ado, thank you very much to Ian Robertson, our mentor extraordinaire and one of the teachers for those courses as well, to finish up this short course. Thanks very much, Ian.
No worries. Thanks, Jack. Just on the matter of exams too, I thought this was a really opportune time to talk about the industry exams in particular. That is the Juniper and Cisco exams that a lot of this material is based upon. The best way to think of those exams is they're usually 60 to 70 questions. They're generally multi-choice. Some of them will be multiple multi-choice. The thing to note about them is the Cisco exam in particular is what's called adaptive. Essentially, what I mean by adaptive is that depending on the answers that you give and the how you're going with the rest of the exam will actually test you more on areas that you're clearly not confident in, which in turn means that while the pass mark required is somewhere on the order of 70 to 80%, the exam puts you at a disadvantage. It essentially handicaps you for any areas that you're slightly weak on. So my general advice is that do as much study as you can before you do those exams. Be very careful of the wording in those exams. They do tend to ask a lot of questions that are, double negatives and similar. So, for example, you might get a question that says, which of these 4 options is least inappropriate or is or similar? Those sorts of things do happen a lot with those exams. And in the event that you do fail, don't be discouraged, because the pass mark required is a lot more than 50% for both the Cisco and the Juniper exams. You will get a printout from Pearson VUE, the proctor for those exams, and in that they will actually list the areas that you were tested on and the relative percentages of those questions that you got right or wrong. So in turn, you can use that as guidance on which areas you need to brush up on more before your second attempt. Both do limit the number of attempts you can take in a given amount of time. And that time does increase over time. So if you fail the exam, you're not allowed to retake it for 2 weeks after your first attempt, for example. And then on your second attempt, if you fail it again, you may find that you're barred from taking it again for, 4 weeks. Those exams typically cost about $150 US. So, they're not particularly cheap, but they are very well recognized in industry. So if you are working with Cisco or Juniper equipment on a regular basis or intend to be, it is well worth considering doing those. I've been asked in the Q&A whether the CompTIA exam is also adaptive. I do not believe it is, but certainly that is a trait that the Cisco exam in particular has. The others generally just have a pool of, several hundred questions that they draw from. So you generally won't see too many of the same questions each time you do the exams. Anyway, we will go on to the material itself. This week, we're covering some of the more advanced protocols that you're more likely to come across beyond layer 3, and those that actually build on what we've covered through layer 1 and 2 as well. We're actually going to start with NAT, Network Address Translation. So why do we have NAT? So NAT is really only relevant to IP version 4, and it comes out of the fact that with a 32-bit address, you've got a maximum theoretical limit on the number of IP addresses of just over 4 billion. The real limit is actually lower than that because there are ranges like Class D space that you will recall from the first week that just don't get used at all. So obviously, that loses roughly a quarter of the space all up. And then, of course, individual organizations don't generally use their address spaces with 100% efficiency. Now, obviously, even if we could use the full address space of 4 billion, there's a lot more than 4 billion people on this planet, which in turn means that if you wanted to give everybody in the world and every server direct internet access with no special tricks, you'd need a lot more than 4 billion addresses. Now, that's where IPv6 absolutely comes in, but not everything uses IPv6 yet. So there's a couple of things that IPv4 uses and offers to address that. The first is there is an industry standard, or what's called an RFC, a request for comments, which is RFC 1918, which describes 3 spaces of addresses that you're almost certainly familiar with in some level, that are only to be used for private purposes, not for routing on the public internet. And those addresses are 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. And they are respectively out of Class A, Class B, and Class C space in the old classful networking ranges. They're not public. Internet service providers will not route them. A lot of internet service providers will use them internally, and that's perfectly fine. But any internet service provider that sees those IP addresses on the public internet will essentially black hole them, will disappear them, stop routing that traffic. And there's a bunch of different techniques that service providers will use to do that. Now, that's where network address translation comes in. And essentially all NAT does is allows a device, typically a firewall or an advanced router, to translate network traffic from a private address to a public address, which in turn means that you can have many, many, many devices. If you're like me, you might have 50 or 60 internet connected things at home. And all of those can essentially be presented behind a single public internet address for the purposes of internet connectivity. So NAT is seen by some as a good form of security because NAT means that only a private device can connect to a public internet. Public internet devices can't connect to something that's hidden behind NAT, at least not without some very specially crafted firewall rules. And because, of course, there's generally a firewall involved in this, there is a general understanding that NAT is, useful for security. That's not really the case. It's really only security through obscurity, and there are absolutely still mechanisms that can be used to defeat NAT and gain access to a device that's hidden behind a NAT gateway or a firewall. So there's a couple of different types of NATs, though, depending on your needs. So the first and simplest form is what's called static NAT or one-to-one NAT. Essentially, all it does is it allows you to convert a public IP address to a private and vice versa. That would typically be used for putting say a web server that you're running in a private office and having it connected through your firewall to the internet and accessible from it. So in turn, punching a hole straight through the discussion that NAT is somehow security. The other form that it offers is actually port-to-port translation, where rather than simply translating everything that comes in from 8.8.8.8 to 192.168.1.1, you can instead say, well, I actually only want this specific service or this specific port to be offered. And that in turn gives you the option and the flexibility to have different services on different servers running on different ports and present NAT through to each of them in turn, because you only need to translate one port to another. Then there's what's called dynamic NAT, which is typically used by larger organizations. Internet service providers use a form of it for what's called carrier grade NAT or large scale NAT. Certain internet service providers now use that as a mechanism to make better use of what is a very limited resource. But more commonly, you'll see it in a large organization, a large business, as a way of allowing multiple computers, desktops, etc., to connect to the internet. Because one of the problems with NAT is that because you've got a many-to-one relationship between private addresses and public, you've got this issue that eventually you're going to run out of resources, run out of connectivity. And eventually there's going to be what's called a collision, where two devices are attempting to talk to the internet. They happen to be using the same ports, which in turn means that NAT can't actually function. So what dynamic NAT does to deal with that is basically use a pool of addresses. So instead of a one-to-one mapping between 192.168.1.1 and 8.8.8.8, you might have a many-to-many mapping where you might have several hundred or even several thousand internal addresses in use, and you might have several hundred external addresses that you have access to. And the mappings are just done sort of on a needs basis then, on a conversation by conversation basis. And then there's what's called NAT overload or PAT, port address translation. Now that's the form that many of you will actually already be familiar with. So if you're using NAT at home, and I virtually guarantee that you all are, because that's the standard way that most home routers and firewalls work, they'll be using what's called PAT, port address translation. They call it NAT, and that's not incorrect at all. It's still a form of network address translation, but instead of translating from an entire IP to an entire IP, it'll reconnect an individual flow based on an individual conversation between, say, your desktop and, well, for tonight, Zoom, for example. So any outbound traffic will just get given a port by that firewall, and that firewall will handle that translation until such time as you hang up from this Zoom session tonight, for example. Now, there's a few terms that are important when you're dealing with routers and dealing with network address translation. There's what's called an inside local address, which is a specific address attached to some device internally. So your desktop's IP address would be deemed an inside local. There's an inside global, which is typically used for static NAT, in particular one-to-one NAT, where you're essentially describing what the outside IP address is for that inside host. There's outside global, which is essentially your router's IP address. and then there's outside local, which allows essentially the reverse connections for static one-to-one NAT. So in typical terms, you will only see inside local and outside global used on most sort of call it consumer to enterprise level firewalls. You'll see the other two, inside global and outside local, used where you're dealing with one-to-one NAT. So if you're running, say, a DMZ or demilitarized zone and have an internal web server that you wish to connect to the internet, you would typically then have an inside global and an outside local as well. So terminology-wise, here's a bit of a diagram. So if we're talking about this device over here, router A, sorry that they're both called router A, I mean the router A on the right, we would have an inside local of 10. Oh, hang on, this diagram is incorrect, actually, my fault. We're talking about the router on the left here. We have an inside local of 10.1.1.10, that's host A. We have an inside global of 55.1.1.1, which is this address here, the public address for router A. We have an outside global of 99.1.1.2. So that's a static address on this device over here, on what should be called router B. And then an outside local of 99.1.1.2 as well, which basically allows for that static one-to-one map between those two devices. So essentially, a couple of errors on this diagram. Router A is the top two. Router B, this one on the right, is actually the bottom one. So one is running what we would call PAT, port address translation. The other is running static one-to-one NAT between 99.1.1.2 and 192.168.1.5. And what that means is that host A, by connecting to the address 99.1.1.2, will actually be connecting to this internal host here. So connections will go through to that router. This router will rewrite the traffic so that it looks like it's coming from 55.1.1.1. It'll go over 99.1.1.2. This router knows that when it receives that traffic to rewrite it so that it goes to 192.168.1.5. And then the return traffic gets rewritten in the reverse direction as well. So this host knows that it's talking to this router when in fact it's actually talking to this guy. And this host thinks it's getting connections from this router, even though it's actually getting connections from this host. So that's a fundamental thing about NAT. It does break the end-to-end connectivity between hosts, and that leads to a bunch of potentially undesirable behaviors. Most applications these days deal with that very well indeed, but it is important to understand that that breakage of that connection exists, because it will inevitably cause some particularly older applications to fail in very interesting and hard to troubleshoot ways. So how do you configure this on Cisco? On Cisco, you basically figure out which is your inside interface. Inside means it's inside your network, and which is your outside interface. And you identify those with a command that's IPNAT inside for the inside interface and IPNAT outside for the outside interface. And you can absolutely have more than one of both. So you can have multiple inside interfaces and multiple outside interfaces, and that's perfectly reasonable. You can then use the IPNAT command, which is actually a global level command, to specify. In this case, we want to do inside static NAT, mapping this address 172.16.1.1, which happens to be an internal private 192.1 RFC 1918 address, to this very public address 203.193.205.50. Now that one command on its own essentially then means that with these other commands in place, any connections to this IP 203.193.205.50 from the public internet will be translated straight through to this internal host. If that host isn't available, let's say you've shut it down or it's rebooting or what have you, that's fine, doesn't make a difference. It'll still attempt to do that translation, and the connection will fail just as easily as it would if the router itself was down. So another way you can do it with dynamic addressing, you can create a pool of addresses where you essentially use instead of the previous command, which was IPNAT inside source, you can instead do IPNAT pool and then give it a name, give it something that's meaningful to you. And then you can define an address range. In this case, we're identifying that everything from 203.193.193.1 through to .50 in what is a /24, 255.255.255.0 is to be used for that pool. And what that in turn means is that any outbound connections will be assigned to one of these addresses in sequence. So essentially, any internal device will just pick up the next available IP address and run with it with no additional config required. And then what you do need to do is you need to create an access control list, which essentially says which internal devices are allowed to use this pool. In this case, we're saying that all of 172.16.1.0 is allowed to use it. Now, a little point of note, you'll notice that this address looks very different to the net mask up here. So there's two different forms of net mask that are used in Cisco devices. So the standard net mask you see here, 255.255.255.0, is a standard network mask. And that's used to allow a router, as we discussed in earlier weeks, to determine which are the most significant bits for routing purposes. In this case, the router is going to care mostly about the 203.193.193 part of this IP address, and it knows to do that with this network here. What this form does, this form of masking does, is it essentially tells the router, well, in this case, we are going to be very strict about the first 3 octets, 172, 16, and 1. And we don't care. The 255 is essentially a binary and. We don't care what that last octet is. So what we're saying in this access list is we're going to permit any traffic at all from 172.161 and then any IP address from 1 to 255 in that last range, or more strictly from 0 to 255 in that last range. And then we apply that access control list here to that pool. So it's a little more complicated than static, but in turn that allows you to be very flexible in how you allocate addresses. Now the form that you're more likely to use at home, you identify the inside and outside, same as you did for the previous two. You create an access list that describes your internal network. In this case, we're using the /24 that is 172.16.1.0. And then all we do is we do IPNAT inside source list 10. This is source list 10 here, access list 10, with a pool of the interface. So we don't actually have a pool. We've only got one address. We tell it which interface we're getting that from. And then we've got this keyword overload. What overload means is that we allow multiple devices to use that IP address simultaneously. And we just hope like crazy we don't get any collisions, as it were. And generally, in a small network, say the sort you might run at home, that's a perfectly safe assumption. Once you get up to a few hundred hosts, it starts to be a bit of a risk. Now, how might you do that on Juniper? Fairly similar. It's in some ways, I guess, more logical, but it is a lot more wordy. Juniper's config is somewhat different to Cisco's in many senses. That's partly because of the fact that if you copy Cisco too closely, they have every right and reason to want to sue you, and that's perfectly reasonable. And also because Juniper have taken a much more, what I'm going to call programmatic approach to configuring these devices. So essentially, though, the way you do it, you actually use security rules. And this again comes back to my comment earlier about NAT not actually being security. But it uses a lot of the functions that a firewall or a security device will have, which is why a lot of firewalls do support NAT. In this case, what we do is we create a source NAT rule. In this case, we want to call it, set security NAT source. We create a rule set that goes from our trusted network to our untrusted network. We define it as being from our trusted zone to our untrusted zone. And then we say we want to match everything. Now, in this case, what we're saying is anything in our trusted network, no matter what, is going to be allowed. And if that rule is hit, which of course it's going to be because, well, 0.0.0.0/0 means literally everything, then we're going to source NAT it to the interface address. So it's more words than the previous versions, but it is a much more straightforward solution. And it means that if you change your internal addresses or if you add more networks to your trusted zone, you don't have to do anything special. And similarly, if your outside addresses change or you need to add additional interfaces to your untrusted zone, let's say you pick up a second internet service provider, again, you don't actually have to do anything for the rules to still work exactly the way you wanted them to. Few commands for troubleshooting, and these commands will generally work on any platform, whether they're Cisco or Juniper. So there's a show command called show IP NAT statistics. Now, what that command will do is tell you what your network address translation engine is currently doing. How many sessions is it dealing with? Who's using it the most? Is it the current Zoom session while you're listening to me talk that's doing the heavy lifting, as it were? And just as importantly, are there problems? Are there any disconnections happening? Are there any collisions occurring? Then there's this command debug IP NAT. Now that will create a lot of logging commands. It'll actually create a whole bunch of extra logs, log entries in your log files on the router. It's really important to be very careful running that command, because doing so will slow the device down significantly, because it'll suddenly get very busy having to basically write down everything that it's doing. It's a really useful command, but should only be done with caution and only when you're actually trying to troubleshoot a problem that you haven't been able to troubleshoot through other mechanisms. And then there's two other commands that are a lot safer. There's show IP NAT translation, which allows you to see what the mappings are between internal and external addresses. And then there's clear IP NAT translation, which allows you to basically remove all of those and force the firewall and all of the internal devices to reestablish connections, which obviously will break things like Zoom temporarily, but is really handy if you are actually trying to troubleshoot a problem that only occurs when you're essentially establishing a connection for the first time. With that, I'll pause for a second and just see what questions we've got.
Absolutely. So we've got a question from Vincent saying, What effects does NAT have on security, and how can businesses best guard against NAT-related weaknesses, such as NAT traversal problems?
That's an excellent question. I love it, particularly with my security background. So NAT itself has really no positive or negative effect on security, any more than an Ethernet router does. It's a form of connectivity. I guess from a psychological point of view, it can be seen as as a form of security, which in turn means that there is a false sense of security associated with it. And the best way to guard against any NAT traversal issues, any hole punching or similar that might occur as a result of NAT, sequence prediction and the like, is to rely on next generation firewall devices to perform that network address translation and to use them as next gen firewalls at the same time. Now, it doesn't matter which vendor you use for that. It really doesn't. But the important thing is that good firewalls will not only do a really good job of network address translation, but they'll also do so in a way that is security aware. So they'll have the ability to do security zones. They'll have the ability to do some form of traffic inspection. since NAT already breaks TCP connections and reestablishes them as a part of what it does, that allows firewalls to do things like TCP sequence randomization in a better way than a lot of operating systems do, which in turn makes it harder for an attacker to use sequence prediction as a way of getting in. And above all else, if you are running, say, static NAT, let's say you are running a website internally, it is a really good idea to have really good logging and auditing around that, and to know exactly what you're allowing in from whom. Also, if you are running NAT and you're also running IPv6, bear in mind that IPv6 does not use NAT. It's a very different protocol. It doesn't need to. With many, 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 many more IP addresses to play with, there's really no call for it. And that in turn means that if you've got excessively permissive rules on your NAT, let's say you've got a permit any in place, if that also applies to IPv6, you've probably got a bit of a problem. So my standard practice is, particularly on a next-gen firewall, permit relatively permissively from your trusted network to untrusted, to the internet. Maybe do a little bit of selectivity based on, say, less desirable websites or known sources of malware, depending on what your firewall offers in that regard. But be very strict, explicit denies on inbound connections from your untrusted networks to your trusted networks. And Shankar's asked, is NAT configured in routers or firewalls or in layer 2 switches? It's almost always, Shankar, a router/firewall discussion. And in routers, it tends to be in your, call them SMB type routers, your small to medium business type devices. Your typical service provider routers, say your Juniper MX series, for example, don't typically support NAT unless you buy some very, very, very expensive hardware indeed. Whereas to use something else from the Juniper portfolio, the Juniper SRX, which is their next generation firewall, supports NAT very well indeed. Conversely, in, say, the small to medium business range, the Cisco ISR range, the integrated services routers that you would typically see in a medium-sized business, they always or almost always do support NAT. They also do support a limited amount of firewalling, generally not to the level of a next generation firewall, such as a Cisco Firepower or Juniper SRX. And it's almost never a feature you'll see in a layer 2 switch, because NAT is very much an IPv4, therefore layer 3 discussion. And Stephen's asked a really good question about CPU overhead. That is, yeah, I love that question, because it's one of those ones where I get to say it depends. Generally speaking, yes, there'll be some sort of overhead in running network address translation, because there's a state table that it's got to maintain, because it's got to remember which connections relate to which inside devices. There's also a bunch of additional logging that's got to be done. There's a whole bunch of other, functions and capabilities that go with NAT. It's hard to put an actual percentage on it, because that very much depends on how the vendor has actually built the router or firewall in question. A lot of hardware devices these days, so a lot of next generation firewalls, for example, that do network address translation, and also do routing, by the way, will typically implement NAT as a hardware function. So they'll actually have built custom silicon that's sole job is to do network address translation. And in turn, that means that the actual performance hit for doing so is really not that measurable. If they have to do it in software, as is the case for some devices, then that can be upwards of 10 or 15%, depending on the use case. Certainly, I'd be, if you're looking at running NAT in a reasonably busy organization, I'd be looking at devices that support NAT as a hardware function, as part of the data plane rather than as part of the control plane. Okay, we might move on, I think. I'll come back to some of those questions. And if I don't get to your questions tonight, please do ask them in the forums, because I will make every attempt to get to them over the next week and make sure that before the forums close, as many of your questions are answered as possible. Okay, now we get to talk about DHCP. So obviously, we've talked a lot about IP addresses. We've talked a lot about networking as a whole, but how do devices actually get an IP address in the first place? So we're specifically talking here about IPv4. IPv6 has very different mechanisms for handing out addresses, but IPv4 has a bit of a problem. It was never designed with scale in mind in real terms. It was designed as a bit of a science project in practical terms, and it was designed in a world where the networks weren't going to be very big. 4 billion addresses was always going to be more than enough for everybody, because it was essentially a project between the US military and a few research agencies. That's clearly not the case anymore. And if you want to manually assign IP addresses everywhere, well, yeah, you can. But if you're running, say, a large enterprise network, with several hundred desktop computers, maybe several hundred laptops as well, you're probably not going to want to manage that by hand. Not to mention the fact that because of the way we typically allocate networks, you're going to need to reallocate that address every time that device moves. If it moves, let's say the person picks up a laptop and takes it home, or they move floors and you're using a different layer 3 network on each floor, you're going to need some way of allocating addresses dynamically. Enter a protocol called DHCP, which is Dynamic Host Configuration Protocol. And it's important to note that it does a lot more than just allocate IP addresses. It's very, very good at that, but it can also tell a device where its time servers are, so where it can get a source of network time from a protocol called the Network Time Protocol. It tells the client where to find its local router, where to find its local DNS servers, potentially where its local Windows domain controllers are, a whole bunch of other things like that that are generally very useful when you're dealing with a very large network. But its main function, and the one that everyone is probably most familiar with, is this function of handing out addresses. And indeed, that's, 99.9% of use cases, that's pretty much all it's used for. Now, the way it does that is with essentially a series of broadcast addresses, broadcast messages, bearing in mind that when a client device first powers up, it doesn't have an IP address, so it can't respond to its own IP address, because by definition, it doesn't know what it is yet. So what it will do is send a message, essentially a DHCP discover message, to a broadcast address saying, hey, I need an IP address. The DHCP server will reply also to a broadcast address saying, well, okay, you want an IP address, here's one for you that you can choose. The client then turns back and says, could I please have that IP address? And then the server turns back a fourth time and says, yes, you can have that IP address. Now, the reason for this 4-stage discussion is because you might, in a very large network, have more than one DHCP server. You might do that for redundancy purposes. You might have a very highly available network that you absolutely need to have things working all the time. And you might have 2 DHCP servers that respond at slightly different times. So what that means is that both will respond to the offer, but the client's always going to respond in turn with a request to the first offer that it receives, which in turn, the fact that all of these messages are broadcasts allows the other server to know that its services are no longer required, and it can go back to just sitting waiting for the next query. So in terms of how that functions, that process is quite important from the exam point of view. Essentially, that 4-stage process again is client does a discovery, sends a DHCP discover, essentially saying, hey, I need an IP address. The server responds with an offer to say, this is the IP address I'm offering you, and here's the other details that you might like to know, such as the router, the DNS servers, stuff like that. The client will then go back and say, yes, please, I'd like that address by sending a request. And then the server then responds with an acknowledgement to say, yep, it's yours, here you go. And then, and only then, does the client actually pick up that IP address and use it. Now, most clients will also, as a part of that process, do a separate check to make sure no one else is already using that address. So they'll send out an ARP request to that address to say, who has this address? Have you seen it? And the reason for that is that obviously you don't have to use DHCP. People can and do, excuse me, statically assign addresses all the time. You'll have someone who's troubleshooting a computer and they'll go and, put an IP address on it. Now, if that IP address is right from the middle of your DHCP network, then the first time that a client goes to use it, there's going to be a problem. So most clients will go back and say, that they'll go and check, they'll use an ARP to do that check. And there's a separate request that they can use, or it's a DHCP NAC, a non-acknowledge, that they can use to say, no, I don't like that address. And then the offer will come back with a different address. So all of these mechanisms have been well thought out in terms of DHCP. Okay, so let's move on now, unless there's any DHCP related questions. I'll move on to WAN. So I'll answer. Greg's asked a question. Why is it over Wi-Fi there's DHCP failures when there's lots of machines? So that's generally a layer 1 and 2 problem, Greg. So DHCP itself generally works pretty reliably, but generally Wi-Fi networks, Wi-Fi is a much more fickle beast than a cable. There's a lot of things that can go wrong. You can have what are called hidden nodes. It's a broadcast medium, so it's much more like a hub than like a switch, insofar as two clients can actually talk at the same time. And when they do, there's essentially an on-the-air collision that occurs. And that in turn, because DHCP is fundamentally based on broadcasts, that in turn can cause a lot of problems. Generally speaking, with DHCP and Wi-Fi though, like I said, it's typically a Wi-Fi issue. And typically I'd start troubleshooting there. There's a bunch of techniques that you can use to identify whether Wi-Fi is the problem, such as, is network performance generally poor? So if you do a large transfer over Wi-Fi, is it achieving anything like the theoretical throughput that the network should be able to achieve? And the good thing is, as you say, the clients don't seem to be phased. That's not surprising to me. DHCP is pretty robust. Generally, if a client doesn't respond in time, or the server doesn't respond in time due to network issues, then the client or the server or both will just retry until they get through. So it might just mean that the client takes a little longer to connect the first time. And Greg's also asked, and this is quite a good related question, best methodology to enforce DHCP. So there's a technique on most layer 2 switches called DHCP snooping. So DHCP snooping allows for a switch, bearing in mind it's a layer 2 device, so it doesn't actually care about DHCP, because DHCP is fundamentally a layer 3 protocol, but it allows the switch to see DHCP requests come out. And part of what it does is it makes sure that a client actually asks for an IP address before it starts using an IP address. So DHCP snooping is the answer to that question. And essentially what it'll do is, if a machine connects to the internet and starts using an IP address that it hasn't been allocated by DHCP first, then the switch will simply disconnect the client, or shut the port, or simply filter the traffic until such time as the client starts to behave itself. Chris has asked reservations. So yes, that's a good question, Chris. What Chris is actually asking is, how do you deal with a machine that needs something approaching a static address? So obviously DHCP, part of what it does is essentially allocate a random address. So you've got a pool. It'll typically be the size of your network. So if you're using 192.168.1.1 as your router address, you'll typically use the rest of that range from 2 through to 254 for your clients. Now, what if you need to know where something is? It's a server, for example. In that case, there's the concept of what are called reserved addresses, where you essentially tell a DHCP server to always hand a particular MAC address, so a particular hardware device, a particular IP address when it asks. So when the server asks, it'll always get the same address no matter what. The server has no knowledge that that's happening. It doesn't need to, but the DHCP server absolutely knows what's going on and makes sure that it always gets the right address at the right time. Okay, that's, yeah, I'll move on to WAN. Okay, so WAN, wide area network, what are they? So there's really two definitions of the wide area network that I'm going to talk about tonight. The first is what I'm going to call a geographical WAN. So let's assume you work for a large university. It might have several campuses. It might actually control the network between those campuses. So it might have its own fiber optic cable in the ground, connecting, say, Wagga Wagga to Bathurst, for example, as is the case for Charles Sturt Uni. And essentially, to all intents and purposes, it doesn't look that much different to a LAN, except that it's much, much, much longer. So instead of, a large LAN maybe being, the size of a building or a few, a large WAN could, according to this definition, potentially connect two LANs together over many hundreds of kilometers. The other, probably more practical definition, though, is essentially one that means that you don't actually own the network that connects your two LANs together. So we might call that a managed WAN, for example. So instead of owning the dark fiber connection between Bathurst and Wagga Wagga, for example, you might lease a connection from Telstra or ARNet or another internet service provider, and essentially use that as if it was a part of your network. So that can be called a leased line, that can be called a managed WAN. There's multiple different technologies that you might use. And yes, we will talk about software-defined WANs in this as well, so SD-WANs as well. Now, why might you want to do this? Biggest reason, you have information that you wish to keep off the internet, that you want to be able to transmit between two sites. So you've got a remote office, let's say you've got a faculty out at, or a faculty office out at Wagga Wagga. They need to share data with Bathurst and vice versa. It might be student grades, for example. You don't really want them going over the public internet in a public way. So you typically have something that looks like an extension of your local area network. And that is fundamentally what a WAN is. It's a way of having a private network that expands beyond sort of the size of a building or a handful of buildings. And yes, a WAN can also define the network that, say, a large university campus might have in between its potentially hundreds of buildings. The other use case, and this is where SD-WAN, software-defined WAN, really comes into its own, is where you're, say, traveling. Let's say you work for a large organization. You want to be able to retrieve data when you're at a satellite office. Let's say your business is headquartered in Sydney, for argument's sake, and you've got a branch office with 3 people in it in Darwin. You want to be able to go to Darwin and connect and use things just the way that you do when you're in the main head office in Sydney. So that's really the reasons why we might do this and why you might care, and why the internet itself is not really the appropriate use case. So what do they look like? So LANs live in buildings, maybe up to a few buildings. Anything beyond that really starts to become a wide area network. The key is in the name. You know, local means sort of local to you, nice and close. Wide area network means anything that's not local, if you will. There's multiple ways to build a WAN. So if you have the wherewithal, and it's obviously a very expensive proposition, you can very potentially run your own fiber optic cabling between multiple sites or multiple buildings and create a wide area network that way. More commonly, though, you're going to talk to a telecommunications provider and lease some kind of service from them. So typically a network as a service type use case. And generally, this is less true than it used to be, but generally the wide area networks of old used a slower form of connection, typically a serialized connection, to connect different sites together. And that was simply a function of cost. It was always, until very recently, it was always cheaper to use a leased line or a serial connection or a modem connection, which is just a specialized form of serial, to connect sites together, because fiber optic cables were expensive. Of course, these days with you know, organizations like NBN or Chorus or BT in various countries providing last mile dark fiber services, it's now very cost effective for a WAN to look very much like a LAN, maybe not quite as fast. You might have a LAN running at 10 gigabits per second or even faster, whereas you might have a LAN that's a WAN that's running at 1 gigabit per second. Now, what do they look like? So there's 4 basic topologies that I'll actually draw up for you. But essentially, they come down to what's called point-to-point. And the simple way to think of this is you've got 2 buildings and they're directly connected to each other. So if you draw 2 buildings and draw a line between them, that's a point-to-point network, point-to-point WAN. So simplest form, very straightforward. You'd typically use a very basic form of routing, or you might just use plain old static routing to do that. Then there's what's called hub and spoke. And the way to think of that is, like the name suggests, think of the spokes on a bicycle wheel. The hub is the big site. Topologically, it's right in the middle of the network. It might not geographically be in the middle of your you might not be based in Alice Springs, you might be based in Sydney, but either way, from the network point of view, everything connects back to it, connects back to your hub, your main site, and then every other site, all of your small sites are connected like the spokes on a bicycle wheel, radiating out from that. Then there's what's called full mesh. There's also a variation on full mesh called partial mesh, which is essentially every site is connected to every other site. And obviously, once you get past 5 or 6 sites, that starts to become really impractical. You can imagine if you've got 600 sites, every one of those sites needs 599 other connections to make a full mesh connection. That's a lot to manage. And even if you're doing it using programmatic means, you're programming it using automation, there's still a lot of things that can go wrong with full mesh. Partial mesh typically involves something that looks a little more like hub and spoke, but with potentially a few of those spokes actually connected to each other, just depending on what your bigger sites look like. And then there's single versus dual homed. Single home sites are hub and spoke with a single hub, whereas a dual homed might be take a bicycle wheel, turn it on its side so you can see both sides of the hub, and you'll note that spokes radiate out to both sides, basically forming a V shape, if you will. Now that's dual home, so it basically means you've got two hubs with each spoke connected to one or potentially both of those hubs. And we'll talk about where SD-WAN fits in all of this as well. Now, in terms of topologies, we'll talk about both physical and logical topologies. And in fact, I've touched on this a little bit already by inferring that you might not have a hub site in the middle of Australia in Alice Springs. You're more likely to have it in a place like Sydney or Melbourne or Brisbane, which is clearly not in the middle of the country. And there clearly you don't have a physical topology that looks just like a bicycle wheel, unless it's a bicycle wheel that's been through a fairly significant accident, I suppose. In any case, a physical topology looks broadly like this. You've got various types of devices, and this is a common way to represent a network. You would logically separate them out based on where they rest, where they sit in terms of rooms in a building, and you show how they're physically connected to each other. You'll notice that nothing in this diagram tells you anything about what IP addresses they're using, what VLANs they're using, how the devices are actually supposed to talk to each other, except in the broadest of terms. But it's still a useful diagram from the point of view of understanding where the cabling runs and what talks to what. So if, for example, everything in classroom 3 was offline, well, I know where I'd be looking as a first instance. And clearly that's going to be the classroom hub. That then separates us out into the logical topology world, where essentially it doesn't look anything like the physical topology, but in a lot of ways it presents a lot more useful information about how the network actually works. So in this case, the logical topology shows we've still got a router. On the previous slide, that was shown as being in a room and connected to a couple of switches. And then we've got these bus type relationships, these bus bars, that actually showed two different VLANs, two different networks, 192.168.1 and 192.168.2. So within those, obviously, we've got a bunch of different hosts as well. So that in turn allows us to really identify from a network perspective, as opposed to a physical perspective, what is talking to what, not just how, but what. In terms of those topologies now, we're talking logical topologies. We've got point-to-point, as I described before, hub and spoke, the bicycle wheel, and then full mesh, which in this case, you can see already with only 6 nodes on it, you've already got a lot of connections between devices and a lot of things that can go wrong. What does point-to-point look like from a network configuration point of view? Well, for one, you can only have 2 ends on it. It's a single line, and a line can only have the 2 ends on it, node 1 and node 2. Nice and simple, nice and straightforward, easy to manage, easy to understand, and fundamentally is the building block for every other form of networking. How that looks logically, obviously, once we connect it up, let's say we rent the connection off Telstra or ARNet or another carrier, we would typically then have a connection to their equipment. It runs through a bunch of their equipment internally that is essentially invisible to you. Now, that might use technologies like MPLS, which we kind of alluded to last week. Doesn't really matter for these purposes because what you care about is traffic getting from source to destination. And then on the other end, your equipment is connected to the telco and comes out in the right form there as well. Logical topology doesn't change. Physical topology, you don't have a lot of visibility of. In terms of some terminology that you would typically need and want to know about, so you've typically got what's called a local loop, which is your local connection to your internet service provider. There's typically a demarcation point or a demarc that basically acts as the boundary, typically on the edge of your building. In other words, everything beyond that point is the service provider's responsibility. Everything on the inside of your building is your problem. And then you have your customer premises equipment, which is typically your router or more commonly a firewall. Different kinds of connections, dedicated connections. These days, while the exams still talk about synchronous serial connections, they're more often than not going to be some sort of fiber. Similarly, you don't typically see ISDN these days in the real world, but you will see it mentioned in the Cisco exam at least as a form of WAN technology. Circuit switched these days is less common for the same reasons. The most common form these days is packet switched networks, where you're going to rent a connection from a service provider that looks awfully like the internet, but generally is private to you. So it's often called an IPVPN. That's a name that service providers will often use, or sometimes a managed WAN. Now, the technologies that you might see used here, VPNs, we'll talk about VPNs more broadly. You can create a WAN using VPNs over the public internet. It's a perfectly reasonable way to go, and certainly very cost effective. It is actually the basis of SD-WAN as well. Then there's what's called MPLS, multi-protocol label switching, which is what a lot of service providers will use to provide connectivity. Now, it is a form of virtual private network as well, but it doesn't automatically mean encryption the way we usually think of VPNs. Metro Ethernet is a specialized form of Ethernet you will often find in cities. So if you're in the middle of a CBD, central business district, and you're trying to create a connection between two offices, a service provider may well use Metro Ethernet. To the end user, it looks just like regular Ethernet, but it is designed to be a little bit more manageable and reliable. And then there's broadband point-to-point over Ethernet, PPPoE. This is the form you may be familiar with depending on your internet service provider. And it can just like it can be used for the internet, it can be used for forming a wide area network as well. Less common these days are frame relay and asynchronous transfer mode, or ATM, not the automatic teller machine. They are older technologies that typically rely on circuits for connectivity. You will see them in the exams, but only in the sense of, are they valid technologies for wide area networks, which they are. And certainly some organizations, finance and security heavy organizations, will tend to still use these. What does IPsec look like? Pretty straightforward. An IPsec WAN or an IPsec VPN, and yes, you can create it as a WAN, would typically use what are called site-to-site VPN connections over the public internet. And as you can see here, this is the start of what you would call a hub and spoke type relationship. So you might have some remote sites, maybe a business partner or something with some routers running VPN software, and they essentially tunnel and encrypt your private traffic over the public internet. Nothing wrong with that, perfectly reasonable way to go. The difference between it and a managed WAN is that with the internet, you have no real quality of service. There's no guarantees, especially when it comes to any intermediaries on the internet. If there's an outage on the internet, it's probably going to cause an outage for you, and you're going to have no recourse. Whereas if you go with a managed WAN, it's typically one service provider that will provide that end-to-end. Yes, you pay a bit more for it, but in turn, there's a service level agreement, which in turn means that if there's a problem, they might have to pay you compensatory costs. They've certainly got a reason to fix it real quick, etc., etc. The advantage, though, of this sort of model is that you can just as easily have a laptop connect in and be treated as an extension of that same wide area network, no matter where they are. Another form of connection is called GRE, GRE tunneling, generic router encapsulation. It's an unencrypted VPN. It's essentially a way of tunneling traffic over an internetwork between two sites using nothing more than IPv4 traffic. And essentially all it does is it tacks on an extra IP header at the front of the packet, so makes the overall packet a little bit larger, and therefore the payload possibility is a little bit smaller. But not being encrypted, it's very, very quick. Most modern routers will do this all day long with no performance impact whatsoever. Trade-off is, by doing that, You're not encrypted, which means anybody can snoop that traffic and see exactly what you're getting up to. We touched on multi-protocol label switching last week. Essentially, what MPLS does is provides a series of labels. So very similar to GRE tunneling in the sense that it adds extra headers and certainly doesn't provide any form of encryption. But unlike GRE tunneling, which is point to point and only point to point, MPLS is designed for anything up to and including full mesh networks. MPLS is typically used by service providers to actually provide their internet networks as well. It has a bunch of features and capabilities that make it very, very useful for that use case. It's two different forms of MPLS, and I touched on this in the forums as well. There's layer 2 MPLS, which allows you to carry layer 2 switched traffic across a network. The advantage of that is that your service provider doesn't need to know or care what your traffic is doing. They can do, you can use it however you want. You can carry IPX traffic over it if you want, IPv4, IPv6, whatever you like, and your service provider doesn't need to know or care. And from that point of view, it makes it very, very easy for the service provider as well. It also means that if you've got particular applications that need to work at layer 2, some custom applications, for example, you've absolutely got that ability there. And there's two different ways that can work as well. You can either provide a switched network, which looks awfully like a very large Ethernet switch, or there's pseudo wire, which looks awfully like a very long point-to-point cable. Then there's layer 3, where the service provider does get involved in your layer 3 network and do the routing for you. There's advantages to that in that they can control how your network traffic goes from A to B, but that same fact could be seen as a disadvantage in many cases as well. Why is it an advantage? Why is MPLS so good? For one, it's very standardized. It works very consistently across multiple vendors, and that's by dint of the fact that service providers really do require it and require it to work really well. It allows you to do some very interesting things with routing called traffic engineering, which allows you to basically select paths based on the kind of traffic you're carrying. So if you've got a really slow but really high bandwidth, high latency, high bandwidth link between two sites, you might want to put all of your lower priority traffic on that and instead prioritize your shorter, faster, more expensive links for, say, voice traffic. That sort of thing is very possible with MPLS using traffic engineering. And another capability is called fast reroute, which allows it to identify when there's been a failure in the network and work around that without anybody actually noticing, except the service provider. Metro Ethernet, touched on that earlier. Essentially, it's just another form of layer 2. It does provide additional monitoring capabilities for the service provider, which allows them to have a service level agreement with you. But from the endpoint, it's just a copper or a fiber connection. So typically, if you're getting a Metro Ethernet connection delivered to you, you'll be just asked whether you want a fiber or a copper connection. Okay, and then in terms of others, there's a few other forms of WAN to talk about here. Obviously, anything that internet can be carried over, a WAN can also be carried over. So some of the technologies that, say, NBN will use, DOCSIS is the standard cable modem, the hybrid fiber HFC cable modem. Mentioned ATM and frame relay already. And then there's PPPoE or PPPo over ATM as well as other options for forming these sorts of networks. A lot of these are a bit older. You're less likely to see them, with the exception of DOCSIS, which NBN is still using. Now, SD-WAN is the interesting topic here. That is, in many cases, just a VPN type connection. So essentially an encrypted tunnel or multiple encrypted tunnels, but with a centralized management engine. So it's You can think of it as VPN, but with the management being done by some kind of centralized software, hence the software-defined component. And in many cases, that'll be done using some form of routing, particularly using BGP. And what it'll do is essentially make sure that the best possible paths are in use, whether that's the internet, whether that's a private network, and so on. Okay. Any questions in the last 10 minutes? Let's
Quite a
see.
number of them. Take your
Beautiful.
pick.
Okay, so Arun's asked a good question about DHCP servers. If there's a DHCP server in a different broadcast domain, will it use a DHCP relay agent? Yes, it will. That's a really good insight, Arun. Generally, DHCP was designed to work within the same layer 2 LAN as the clients. But obviously, if you've got a very large network, that doesn't scale very well. So most switches, most good switches at least, or most higher end switches, and most routers support what is called DHCP relay, where they essentially see the DHCP packet and act as a DHCP server, sending the query through to the real DHCP server, which then figures out which address to hand out and replies accordingly. That's not actually covered in these level exams, but it is a very useful insight to know. And certainly if you're managing even a moderately large network, it's useful to know that there is this DHCP relay function, and that's a really handy way to put all your servers in the one place. You might have a server network. It's generally considered best practice these days. And you'd have your clients on a separate network, and you'd use the switch or the router as a DHCP relay between the two. And Jacob asks a very related question. As a DHCP service based on broadcast, is it limited to a single broadcast zone? In short, yes, unless you use a DHCP relay. DHCP only works within a single layer 2 broadcast network. Good insight from Bijal, and I apologize if I've mispronounced your name, of course. Does a connection from home to an ISP technically characterize as a WAN? Yes, it does in a lot of ways. And yes, you're right. A lot of service provider routers will label the outgoing port as a WAN. As I alluded to, there are a lot of similarities between a WAN, which I would typically define as being a connection between two privately owned networks, and the internet. And in fact, you can run a WAN over the internet. I think the reason most sort of particularly consumer to prosumer grade equipment has this concept of a WAN port is because WAN fits very easily, in the space above the port itself, and is generally well understood. So yes, I would consider it a wide area network in a strict sense, because it is a connection to a larger geographic network. Do you need separate public IPs for remote sites for IPsec, says David? You don't need separate public static addresses for the remote sites. As long as they have a public address and therefore can talk to the internet, bearing in mind that private addresses won't be carried on a public internet, then they can connect from those sites into a statically defined hub. The clients, the spokes might be dynamic, but the hub has to be static in some form. Now, if it's a completely private WAN, you don't need any public addressing at all. So if you've got let's say you've got two offices and you're connected via, say, Metro Ethernet or a managed WAN from a service provider, there doesn't need to be any public addressing in that space at all. And in fact, there's a good argument for not using public addressing there because, well, it's a little bit wasteful. How extensively is MPLS still in use, Jason? And what technologies are replacing it? Within service provider land, MPLS is still broadly the technology of choice. There are not, to my knowledge, a lot of options looking to replace it the way There were enough for ATM, for example. ATM was more or less replaced by MPLS, and MPLS still very much has its place. Extended and expanded a little bit by techniques like segment routing, which is absolutely outside the scope of this course. And there's an associated technology called SRv6, segment routing on IPv6, which doesn't use MPLS at all, but provides very similar technologies. Most service providers are still very heavily in the MPLS space, but SD-WAN is a lot cheaper than a managed WAN, because with SD-WAN, you can go and buy regular consumer grade internet connections, maybe 2 or 3 of them, because one of the advantages of SD-WAN is that you can use multiple links, and you'll probably still be better off than buying a managed WAN, as well as potentially having a more reliable environment. Now, in doing that, it basically means that the reason that a lot of service providers use MPLS starts to go away. Now, will that mean that the service providers get rid of MPLS for their internal use? Probably not, in my opinion, because it is still very, very useful for managing traffic flows within a service provider network. They might eventually move to, say, SRv6, segment routing v6, but these are big, heavy networks. They don't turn on a dime, and it'll take a fairly significant shift for them to move. Unlike ATM, where that was basically that switch from ATM to MPLS was largely driven by technology changes from ATM to Ethernet, where SRv6 still uses Ethernet, so there's still absolutely use cases for using MPLS in that as well. Does IPv6 and NAT together make it more difficult? It depends. Generally not, and there's my answer again. Generally not. IPsec does have some capabilities that allow it to traverse NAT very effectively, and most good NAT firewalls will be IPsec aware. They'll recognize an IPsec connection. They might not be able to decrypt it, and you probably don't want them to, but they'll at least know what it is and know not to mess with it, as it were. They'll do the minimum required to make it work and no more. The challenge there, though, with IPsec and NAT is that the connection can only be from inside the NAT environment, i.e. inside your network, to the outside. Obviously, the remote side can't connect inside unless you're using static NAT as well.
All right, Ian, I might just give you 1 longer or 2 shorter questions before we've got to wrap up for time.
Yep, no problem. I was just about to say that. So Shankar, you've asked me to explain a little more about SD-WAN. As you've just heard, I don't have time, unfortunately, to do that right now. But if you'd like to pose that question in the forum, I would love to give you a much, much, much longer answer there. And then the last question I'll answer is, and again, anybody who I haven't gotten to, please don't be disheartened. Please go and ask on the forum, and I'll be happy to type away madly and get as many answered as I can. But Oluwa has asked, WAN versus MAN, what is the difference? So wide area network versus metropolitan area network. Essentially, geography is the real answer here. So a metropolitan area network would typically be limited to the size of, say, a city, whereas the geographic definition of a WAN really has no upper limit. You can have a WAN that crosses continents. So typically, I would not use that differentiation all that greatly, but if you did see it come up, then a metro area network covers a metropolitan area and not much more than that, whereas a WAN can be any size from building to building to city to city.
Great. Thank you so much. And everybody else as well. Sorry to everyone whose questions weren't able to be answered for time reasons. Thank you so much for asking them. And hopefully you will have plenty of time and opportunity within the next week before the forums close on that learn.itmasters.edu.au portal to have these discussions with Ian and with each other. Is there anything that you would like to say to finish us off, Ian?
I would just thank you all for your time and patience, especially those who've stayed up late or gotten up extra early. It's a huge commitment to make, and I do appreciate it. I would ask, and just to reinforce what Jack said earlier as well, please do fill in those surveys, make them statistically significant for us, please, because that's how we make these courses even better moving forward. But otherwise, I wish you all the best, and I hope to see you again either in one of my IT Masters subjects or at another short course.
Fantastic. Thank you so much, Ian. And thanks to everyone who has participated, who's asked questions and joined in on the chat as well. We really appreciate your engagement. Again, please do visit that IT Masters portal, that learn.itmasters.edu.au. That's where you're going to be able to find the recording of this session, the recordings of the 3 prior sessions over the last few weeks, the quizzes, other learning materials, the exam, etc. So hopefully we'll have plenty of robust discussion about the course content that we've covered. Those forums, like I said, will be open and available to you for the next week. There will also be the exam. So the exam will be available to you within about 48 hours from now. That exam will be available indefinitely. Once you complete that with a pass mark of 50% or higher, you've got one opportunity to complete that over 60 minutes, 1 hour. It's a multiple choice exam, and thanks to Ian as well, there shouldn't be any trick questions involved in that. Once you've completed that, and if you pass with 50% or more, your certificate for completing the short course will be available to you within 7 days from that time. Again, we do really encourage people to fill out that survey, which Lily hopefully will be able to just drop the link to in the chat. Thank you, Lily. Just answer a couple of quick questions about your experience undertaking this course. It's really valuable feedback for us to continue developing and improving all of our different short courses. Feel free, of course, to take as many of our short courses as you would like. You can find them on our website at itmasters.edu.au, which is also where you can find the information on our full-length graduate certificate and master's programs, some of which include subjects taught by our wonderful mentor for the last few weeks, Ian. We've got a variety of those. If you are wondering if you're eligible, or if you're eligible for course credit to shorten the duration of your course or for reducing the cost of the course, you can use the eligibility, I'm getting tongue-tied. The eligibility link, which Lily has once again extremely timely posted in the chat again. You can fill in our form, and one of our wonderful eligibility consultants will get in touch with you to talk about your course options as well. The quiz for this lesson should be available within about 24 hours via that learn.itmasters.edu.au portal as well. Thanks everyone for a fantastic course. Thanks so much once again for your participation. Thank you, Lily, for assisting and making sure everything runs smoothly on the back end. And thanks so much to Ian for being such a fantastic mentor, for being so engaging and informative for everyone. So,
it's been a pleasure. Thank you.
It's been absolutely a pleasure for us as well. So once again, depending on where you are in the world, good morning, evening, afternoon, or night. And hopefully we'll see you again in some of our short or long courses in the future. Thanks, everybody, and take care.